asking whatever you want if something's not clear. Don't let me drone on the whole stuff. So yeah, I want to talk about the lambda calculus, and we could state it, pretty easily and quickly. But I think the most helpful thing is to give you a lot of background and context as to sort of where it comes from, because I think it makes a lot more sense when you understand how it came about. Oh yeah, so the slides are available on GitHub if anyone wants to look at them. It's just my name, and then you should be able to find it. Right, so first of all, what is the lambda calculus? It's a model. It's a formal model of computation. Right, and we have lots of them. We have the lambda calculus. We also have there's another one called the new recursive functions. Sometimes it's called general recursion. You can find them. It's not too bad. It's pretty intuitive. Probably people are more familiar with Turing machines. A man named Emil Post, right around the same time, came up with a very similar idea. Another one called Post machines. And you can notice these are all like around 35, right? And then later trickled in some more like formalizing flowcharts. We actually turned that into a full Turing complete formal model of computation. Register machines are actually closer to what we really, people say Turing machines. A lot of times in your mind, you think it's a register machine. These are all explaining what computation is. Taking a step back, people have been doing computation for a long, long time, well before computers, right? The Babylonians had, cuneiform tablets where they told you how to do division. Like Knuth has this paper where he talks about how old some of these algorithms are. And people are describing all kinds of stuff for ages. And we have strong intuition what we mean when we talk about computation. There's like when you're following a recipe, cooking or something, you know if there's a missing step, what's missing. We know what computation looks like. We have real strong intuition. So what was going on in the 1930s that all of a sudden we get all these formal models? So I think for that to make sense, you have to step back into the previous century, what was going on in mathematics, because that's really where all this comes from. So in the 1800s, there was this huge explosion of mathematics. Essentially, people figured out a lot more abstract ideas and new proof techniques that allowed them to prove a lot more things. Things that have been holding people back for a long time were suddenly proved. But these proofs, they were a lot more abstract, and also somewhat less attached to the sciences. So strangely, back in the day, math and physics were so related that you could almost test out, like if you thought you figured something out, you could almost write the equation down and test it, see if it worked. Today that might sound kind of weird because we're used to taking math class and seeing how detached it is from science. But in the 1800s, the beginning of it was very attached to science. And in fact, even the proofs where it would be something like, you might have a theorem that says, you have an object A. If you have an object A, there is some other object B. Back in the day, those sort of proofs would be more like, here, I'm going to take your A and I'm going to show you how to transform it into a B. And it's going to be real constructive. I'm going to show you step by step how to do it. That became less true in the 1800s. So things like non-constructive proofs, what do I mean by that? So instead, a theorem in this age might be something more like, well, assume there was no B. I'm going to show you how that leads to absurdity. So you're not left with knowing what B looks like from A, you just know it has to be there, right? It's this sort of double negation where really you sort of proved not B. You showed that it's not the case that B doesn't exist. And then you infer B, but that leaves you with this lack of knowledge as to what B even is, how it came about. And at the same point in time, you also have the rise of first order logic right at the end of the 1800s by American Charles Sanders Peirce and German Gottlieb Frege. So if when you took calculus and then you saw the definition of continuity where they say, for all epsilon greater than 0, there exists a delta. That language, for all there exists, are quantifiers. That's the missing piece to logic, this first order logic. That's the missing piece that they filled in, Peirce and Frege. And this is a really descriptive language to where now it would look like logic was starting to be more expressive to express math. And so right at the time, as all these proofs are becoming abstract and powerful, and logic is becoming more expressive, is right around when it began a big debate about what should a math proof look like? What are the foundations of math? The Greeks are obsessed with this idea of potential infinity. So for the Greeks, they didn't like actual infinity. What's actual infinity? Say you wanted to talk about all the natural numbers together. That's an actually infinite object you're wheeling around. The Greeks didn't want to do that. They said it's fine to talk about numbers as potentially infinite. Any number you have, there's a bigger one somewhere. And that's fine. This process that we all know is infinite, that's fine. But don't go collecting it in one object that you can manipulate. And it turns out people started wanting to do this, use these actual infinite objects as you discover more things. There was a debate about what's more foundational, sets or functions. This is right at the time that set theory is kicking off, and maybe Bertrand Russell discovered some paradoxes. Have you guys seen Russell's paradox? There's fun versions of it, like there's this barber who shaves everyone who doesn't shave themselves. And then you ask, does that barber shave himself? Oh, if you did, you shouldn't. If you didn't, you should. So Russell did that in set theory, and they had to go back and figure out, okay, well, how do we salvage these sort of proofs? His solution at the time was types. And this is types for programming languages. This is actually where it comes out as a potential solution to some paradoxes in math. So people start asking, what constitutes a proof? And if you think about a proof, you might need to be clever to come up with a proof. It might be, there's some hard theorem and you use some clever idea to come up with a proof. But once you've come up with a proof, it should be easy to check the proof. Maybe it's not in practice. But the idea with a proof should be anyone can look at that proof and step by step say, yeah, it's correct. So right out of while people try to figure out what a proof is, they start wondering what an algorithm is. All of a sudden, they need to really solidify what an algorithm is because it's important for what a proof is. A proof is something that you check. You shouldn't have to be smart to check a proof. And then in 1910, is this sort of a lightning rod moment where Whitehead and Russell, the same Russell from Russell's Paradox, they put out this book called The Principia Mathematica. And this book was interesting philosophically, it was interesting mathematically. Philosophically, there was this position that people said, hey, you can reduce all of math to logic. And people said, no way, it can't be done. And this book was attempting to do it. It attempted to be way more rigorous than anyone had ever been before in mathematics. And it went from just logical axioms, step by step. I forget what the famous anecdote is. It's like he proves 1 + 1 is 2 on some way far out page. But this book, and even though the notation in this book is horrendous and no one uses it anymore, and even though it's not very easy to read, no one reads it anymore, the ideas, it really encouraged everyone to try to do this more formal notion. And it inspired a whole generation of mathematicians to take it seriously. So it's right around this time that church actually does introduce the Lambda Calculus. You're used to functional programming, heard of the language Haskell, or maybe you've heard of this technique in functional programming called currying. This comes from the man named Haskell Curry. He was inspired by the Principia. He saw something that was wrong with the Principia. It had to do with this real fiddly detail that I'll show you in the Lambda Calculus. And he said, that's wrong, I think I can fix it. Inspired lots of people to do it. And for church, really where the Lambda Calculus made its shining moment, its contribution to mathematics was really in this solving this problem of Hilbert's called the Untitled problem, which just means the decision problem. And this problem was to say, can you give me a statement in first order logic, just a formal system, and have an algorithm that can say, yes, that's true, or no, that's false. There was a lot of hope, humanity up until this point probably thought that this was true. Math seemed like something that this could happen to, where you have this machine, you just crank the machine and it cranks out true theorems, and all the true theorems. But this proves what church showed was that the Chinese problem is not solvable. There is no algorithm that can look at one of these formal statements and say, yep, nope. Very closely related to Gödel's incompleteness theorem. Very related to the halting problem, if you've seen any of this, Turing's halting problem. In fact, Turing has an equivalent version of this too. Yeah, so this is sort of the end of the background to it, sort of where Lambda Calculus comes out. So you see, it was sort of to address this sort of crisis in mathematics. It was more to do with formal logic. But lo and behold, it ends up inspiring programming languages, mostly functional ones, right? So Lisp is hugely inspired by Lambda Calculus. So it was Algol 60, ML, Pascal. And in fact, even the Principia Mathematica itself, like if you've done functional programming, maybe you've heard the term referential transparency, people talk about that. So that term was coined in the Principia Mathematica. So through its influence in the Lambda Calculus, a lot of stuff that we take for granted, in these functional languages came out of this time. Types. Right? So let me tell you what the Lambda Calculus is now. So first I'm just going to sort of build up some intuition. This isn't exactly it, but this will get us pretty close. So, well, first of all, any questions or we'll go on? Yeah. All right, so in math class, usually this is how we write. Like, oh, there's some function f, has two variables, and here's what you do. And we all know that if someone tells you computed at f of 1, 2, you just plug them in, right? You got your eraser, you erase x, draw on a 1, you erase the y, draw 2, you can't really do that. This is the standard way you write this. This is another kind of similar one that you'll actually see. This is sort of the anonymous version of it. So I'm not going to give it a name. I'm not going to say it's called f, but I'm just going to tell you, well, x and y map to that thing. And 1 and 2 map to that. And under this mapping, we might say, well, under this mapping, 1 would be mapping to this function, 1 squared plus 5. Then I got to tell you, well, why is it 1? Right? Now this is really close to the Lambda Calculus. The Lambda Calculus doesn't actually have plus and exponentiation in the syntax. We built it in. But this is really close. So instead of just saying x and y map to, we use this lambda x to say, this is a variable. You can plug stuff into it. Y is a variable. You can plug stuff into it. And here's what it is. So this is like a function. And then if you want to apply it to say the value 1, well, you just erase the, get rid of the lambda x, because now we've applied it. Erase the x and plug it in 1. And then you can apply this thing to 2. And this is notation. It's very similar to the actual Lambda Calculus, and now we're just going to strip it down. So, lambda terms. You can think of lambda terms as programs in Lambda Calculus. And really, you only have 3 things you can do. You can state a variable, like x, y, f, steaming coffee. Doesn't matter what they are. You just have to recognize them as variables. If you have a term, you can make an abstraction. That just means state lambda and any variable you want, dot in front of the term. And if you have 2 terms, you can stick them together. So this abstraction is like saying, I'm going to turn m into a function of x. And you can think of application as applying the value n to the function m. I'm playing a little loose with parentheses here, but I don't think it's that confusing. I think it makes sense when we do it. So let's look at some examples. So this is I for the identity function. So lambda xx, you give me an x, I return it. I wrote it here again with coffee cup. Just to say, it doesn't matter what you call the variable, right? Formally, people like to be a little more careful, and they say these terms are alpha equivalent. But just letting you know stuff you'll see, it doesn't really matter. The intuition is correct. It doesn't matter what variable you use. These are the same function, formally speaking. Here's some other lambda terms. They're all famous, but it doesn't really matter. K, you can see this says, give me an x, give me a y, and I return x. It's not exactly like the first element of a pair, but something similar, right? S is another lambda term. This omega one is fun because it has some bad behavior. We'll see in a minute. And this is the famous Y combinator. It's helpful for defining recursion. And this is an example of that. So in order to really use, so here I've told you what the programs look like. They look like these. Now let's see how to run the programs. So in order to do that, I have to talk about substitution. Remember earlier when I was talking about erasing the x and drawing into 1? That's what substitution is. So say we have a term m, and maybe, maybe not, it contains some of the variable x, and we want to do another term n for it. So that's how we write it. m with x substituted for m. So what would that look like? So you got x, stickman x, and I want to make x a coffee cup. Coffee cup, I told you was a variable. It could be a whole term, whatever. Keep it simple. Anyone want to guess what this would be?
Coffee cup, stickman, coffee cup.
That's right. Happy stickman. That's what that's that. And here's just there are sleeping dragons here. Watch out. This is the thing that Haskell-Curry found that was wrong with the Principia. It's way more finicky than you realize. A lot of these little gotchas. So I'm playing fast and loose so that you guys get the good intuition. But just know that if you read a book, they're going to be way more careful because over history they've found all these little persnickety things that sneak in. So here's a gotcha, right? Lambda yx. This looks like, hey, give me any y you want, and I'll return x. Oh, now we go and substitute x for y, and lo and behold, we have the identity function, which seems way different than this thing. So this is capture avoiding substitution.
When would you use a substitution?
Excellent question. Next slide. You would use it when you have a regex. A regex is just a reducible expression. So you have these two terms next to each other, and one of them is an abstraction. One of them has a lambda x. And then you can do substitution. So this is called beta reduction, and it's written this way. Here we got our regex, and it beta reduces to substituting in for x. So we got lambda x stickman x, and we apply it to coffee, and we know what that beta reduces to.
X would be x subs for coffee.
Say it again?
X subs for coffee.
Yeah, exactly, yeah. So we just plug in the coffee cups over x. So here it was a function of x, and now we've applied it. So the lambda x is gone, and the x's are all now coffee cups. That's it. That's the lambda calculus. And we can do a bunch of examples. You thinking, Britt?
Huh?
You thinking? Does it make sense?
Yeah, I mean, kind of. You go ahead.
So let's do an example. This is sort of another famous example. This is from like the 1920s or something. So SKK, these are the ones I defined before, but here they are again. You can tell I swapped out variable names because I don't want them to clash. Another thing I'm sort of playing fast and loose with here, but it's okay. So here's a regex. I got a lambda x and a term, and I got another term. So what do? Well, I'm going to erase this lambda x, and everywhere I see an x, which is only here, I'm going to take this blue thing and plop it over that x. Bam. That's it. Beta reduce. And we keep going. Clear? Here's a regex. Now here's something interesting. There are actually two regexes here. There's this inner one, and there's this outer one. And in fact, this is something we'll get back to near the end of the sort of the theory part before we use some Python examples. This turns out to be a really important distinction. In fact, if you've ever heard the terms call by value and call by name used, you might know that Python isn't technically call by value. It's call by reference, blah, blah, blah. But let's just think of Python as call by value. What does that mean? The intuition is if you pass a Python function a parameter, it evaluates that parameter before it enters the function. That's kind of like this here, where we're evaluating this before we go outside. This is sort of innermost reduction. Whereas other languages, maybe you've heard of languages as being called lazy. Haskell people say it's a lazy language. This is the sort of call by name, where you're happy to pass parameters into the function before you evaluate them. This is just the intuition, but anyway. So notice that there's a couple of choices here. That may make you think, this is kind of crazy. We'll get to that later. So we're just going to go merry along our way, beta reducing. So here we got a lambda y, we look for our y's, up only that one, and we took the blue and plugged it into the y. Clear it. Now we'll go a little faster. Here's a regex. I spotted one, and then I pointed that z into the a, and then we go right to a. It's real mechanical procedure. A little hard to read, but pretty straightforward. There's another one. There's another one. Does anyone recognize this friend?
Yeah, there you go.
Bam! So SKK is I.
So how did you know for the second set of parentheses at the very top that that needed to be substituted for x? How did you know x was the variable or,
Great question. And this is something I sort of glossed over a bit because it's the outermost one. Technically, if you've seen functional programming languages before, you've heard about currying, whereas you tend to think, well, you say, oh, I have a function of two variables. I'm going to pretend it's really a function of one variable that returns a function that takes a variable and returns the answer. So it's x because that's the outermost one.
And then, sorry, go ahead.
We're probably gonna, same thing, so I guess the C to lambda DC, that's basically the second variable. And
Exactly.
Okay.
Yeah.
100%. Yep, that's perfect. But from Lambda Calculus point of view, it thinks everything is a function of one variable and just returns a function that takes it.
And takes into whatever the next
Exactly. So this is sort of our
outermost variable is work its way back in. Yeah, okay.
exactly. Yep. And this is actually done, in the 1900s, like right after the Principia by name and Moses Schoenfield. It's called currying, but it shouldn't be called that. But this goes back to the
I was going to ask, is there a way that you can read that in English? Like, does Lambda Calculus have
No.
no?
No. Not really. We'll see some Python examples and maybe, but not really. It's mostly string manipulation. It just happens to work and have interesting properties. So that's crazy. So here's one. Here's omega. The fun thing about this guy is it reduces to itself, right? So we remove this lambda x and then we stick this thing and put the x up, we're back where we started. So that tells you that this beta reduction is not necessarily well behaved, right? This is an infinitely running program. This is an infinite loop. So yeah, so here's how we can actually start defining arithmetic and other stuff in the Lambda calculus. So there's no reason to think that you would ever come up with this, but it works. That's how I think about it. Maybe there's some intuition we can talk about, but so how do you define zero? Well, zero is the lambda term that says, give me a function, and I'm going to ignore it and return you the activity function. Okay, that's weird. Whatever. What is one? One that says, give me a function, and I'm essentially returning that function. Lambda x f of x is just f, right? So give me a function that I apply once. What's two? Here's where the pattern starts to become more obvious. What's two? Two says, give me a function, and I return the function that just applies f twice. So what is, these are called church numerals, for defining numbers this way. So what's 17? Well, it says, give me a function, I'm going to apply that function 17 times, right? You can define the +1 function successor, saying, give me a church numeral n and a function f, and I'm going to first apply it n times and then apply it one more time. And you can define plus, it says, give me a church numeral m and n and a function f. Well, I'm going to apply f n times and then apply it n times. And it just works. So this, you don't need to read for like clarity. I don't think I made a mistake, but I totally could have. But this is sort of this is just so you can sort of see the mechanical nature of it. So this is 1 + 1, and you just chug the rules on down, turn the crank, and it turns into 2. So it works, at least for plus and 1. And now we'll do a little bit more exciting example. So the goal here is we're going to get to the factorial function defined by recursion. So I'm going to show you how you can implement recursion in the Lambda calculus. So this uses the famous Y Combinator, hacker use. So here's the definition. Whatever it is, it works. Okay? You don't have to follow this along. You just have to believe me that I did my best to try to not make errors. So if you take this Y Combinator and you apply it to any old random f, I claim you beta reduce to this right here. I also claim that if you take f, y of f, and you beta reduce, you end up with this bottom line here is the same as this line here. Something I'm not going to talk too much about is beta equivalence. You can think of beta equivalence as just saying that two terms are beta equivalent if they reduce to the same thing, right? We think of 1 plus 1 as being the same thing as 2, more or less. You just have to finish the computation. Well, imagine beta equivalence is that same thing. They're essentially the same thing. So the point of this is that for any f, the y combinator of f is beta equivalent to f of y of f. That's why it's called the fixed point. So what's a fixed point? Take yourself out of Lambda Calculus for a moment and just imagine what's a fixed point on, say, a function from natural numbers and natural numbers. That's just like say it's g. A fixed point of g would just be some number n, so that g of n is n. Right? It's where it crosses the line y equals x. So here you see f of this thing is that thing. So it's a fixed point. So y says, give me any function you want, and I will find you a fixed point of that function. And that's how we can define recursion. So it's factorial. It's this guy you've probably seen here before, this thing here. So factorial of some number n is just that number times all the numbers below it. To be precise, what I wrote below, I should probably have 2 1s, but it looks pretty good. So here's a definition you probably get in math class. Factorial of n is 1 if n is 0, or n times the previous value if it's not 0, right? Standard little recursive definition there. Now we're going to define it in the Lambda calculus. I didn't tell you what int is, if then else, but you can imagine, just like we defined plus, I can show you some other magic Lambda terms that give you if then else. An is 0 function, I didn't even tell you how to do booleans yet. We'll do that on the next slide. There's the church numeral 1, multiply. The only thing that's sneaky here is f is the name of kind of the factorial function I'm defining. What is this little f? This little f is saying, I don't know how to do recursion yet. So I'll just give me the function that lets me call myself. I don't know how to do that. So pass in f, and here's where I'm sort of calling myself, but not really. And then here's the magic trick that makes it work. We define factorial to be y of f. Why does that work? Well, let's do it. So let's look at factorial of n. By definition, it's just y of n. Before, hopefully I somewhat convinced you that it's beta equivalent to f y of n. Well, we know what f is. I wrote f right here. So let's just write it out with its definition. So it's if then else is 0 in, return 1, otherwise multiply n by the rest. But now, here we have yf, we place it after the left, right? That's where the magic happens, because what is yf? It's factorial. So now you have factorial of n defined by recursion of itself. Pretty cool.
And people were doing this before computers?
Yeah, absolutely. Yeah, they wanted to, yeah, absolutely. That's right.
What was their motivation?
Hmm?
What was their motivation? Were they trying to solve a specific problem or just learn?
Yeah, they were trying to formalize math. They were trying to formalize proof structures and math and constructions and all this sort of stuff. They just needed a more rigorous basis than they had before.
And they went down to numbers. That's great. And they even defined numbers.
Yeah, numbers. And well, here and now, we also get this basic predicate logic. So you can define true. Why is that true? Well, it works. False, and, or, not. Here's your if then else. Here, and true is this, and it just reduces down to this, which lo and behold, that's false. So true is sort of like projection on the first coordinate, false is like projection on the second. Think about that as pairs. So now we have basically Boolean logic, we embedded all this stuff. So that's kind of the end of the examples that I was going to show. And then I was going to sort of go back to sort of an interesting theoretical result about the Lambda calculus. It says, earlier I mentioned where we have this choice of a redex, and I said, oh, there's, we can pick this innermost redex or this outermost redex. But you might be wondering, like, maybe this whole thing is broken. And if you reduce one way, 1 plus 1 is 2, but if you reduce the other way, 1 plus 1 is 3. Then it's completely useless, right? So how do you know that the computation is meaningful if I need to tell you how to pick the redexes, right? So the next thing I want to talk about is sort of the answer to all those questions about, well, the main idea here is normal form. I've been using this without really giving it a name. But you know, when I said 1 plus 1 plus 1, 1 was 2, if you go back to it, there were no more redexes at the end. It stopped. The computation stopped because there was nothing else to reduce. And that's what you call a normal form. A normal form is just a lambda term that has no more redexes. You can't do anything else. So the question that you want to know is, well, when do they exist? We know they don't always exist. We saw that omega thing that reduced to itself. So it never stopped. Are they unique? What if 1 plus 1 is 2 or 3, depending on if you're in Python or Haskell? That's not good. You know, what does it matter? Does it matter at all what reduction strategy you pick? So these are the questions floating around in your head. You see this? And then the Church-Rosser theorem is the theorem that answers these questions for us. That's a fundamental result. So it says, I'm going to explain what this notation here is. If I could have figured out how to put a little beta subscript on the end of this double-headed arrow, I would have put it in time. So this says, you got some term x, and you go about beta reducing it a bunch with your favorite reduction strategy. You end up with some other term y1. And then somebody else, you know, your best friend comes along, and they have a different reduction strategy. And they end up with a different term, y2. The Church-Rosser theorem tells you that you can always find another term z that they can both find their way to. So the reduction strategy kind of doesn't matter. The corollary to that is if a normal form exists, if the computation stops, it's unique. 1 plus 1 is always 2. You don't have to worry about that.
Is there a way to go from z back to y2 and y1 and then to x?
Probably not uniquely. Maybe. I don't think uniquely. Yeah, no, definitely not uniquely. Because if you have 2, you don't necessarily know if the program started with 1 plus 1 or 0 plus 2.
Yeah, so you and your friend have both decided to reduce x.
Yep.
You get y and y1 and y2.
Yep.
You know that it's not normal form yet, so that there is a z.
That's a good point. Yes. If y1 was a normal form and y2 is a normal form, then this theorem essentially tells you that this is not doing anything. It can't reduce. So it's like the no-op, and that these have to be equal. Or they're not in normal form, and you continue along. And yeah, z might not be a normal form. Z may still be divergent. All it says is no matter how far out you go one strategy and how far out you go the other strategy, you can always find common ground. That's a good question. And then I'll just briefly, this is sort of the end of the theory part here, say there are names for the reduction strategies. Call by value is the sort of intuition, well, technically it's reducing the leftmost, innermost redex first. So this is like reducing the parameters to a function before you pass it to the function, like Python. Call by name is more like the lazy evaluation. Technically Python is called by name, but it's like that one is the one where you can pass in arguments before you evaluate the function. You only sort of evaluate them when you need them. Call by name is this optimization, because you can imagine call by names kind of not optimal, right? Because what if you pass something that takes a long time to reduce into a function that replicates that thing in lots of places? Well, it would have been nice to have computed it once instead of everywhere. So call by need just says, well, we won't evaluate, but when you do evaluate it, remember where else it was so that you can plot in the computation. This is what Haskell does. And the last theorem here I'll mention is theorem that says that call by name always finds a normal form if it exists. So if the computation does call by name, you will find it. It's not true that call by value will find it. And this is kind of obvious, right? So you know that term, that omega term, that when you try to reduce it, it just reduces infinitely. Imagine a function that takes in a value and does nothing with it, and then just does something nice. If If you pass that in omega, if you try to reduce omega first, you just loop forever. If you don't try to reduce omega, then you ignored it anyway, so it didn't matter. That's kind of the intuition as to why. Call by value could fail to call by name. And yeah, then I was going to do some Python examples. Let's see what time it is. Any questions on it? It is 6:18. We're still pretty good on time. Questions? Okay, cool. Let me show you some Python.
Well, Jared fires up his Python. There are a couple. There's an interesting programming language called Urbit, which uses church numerals. So you actually can use functions to represent numbers. It is god-awfully slow, but it reduces and actually works.
And there's another one too called, I think it's Cydia, like the C with the thing. It's another interesting program. So this is plain Jane, Python 2, Python 3. It looks funny, but I swear I didn't import any library, I didn't do anything weird. This is just using the Lambda notation from Python as is. So, you want to dim the lights? Or is it readable? Ish. Not really not. Sweet. Oh, perfect. Oh, perfect. Good. So if you were to like go on Wikipedia and look at Lambda terms for true and false, you could type them right into Python just using this sort of translation. When you see lambda x dot, just write lambda x : and this would, so this is the lambda term for true. Python lets you do, like Python would let us say add x plus y. Lambda calculus, well, Python would. Python's languages are a little bit more generic, or quite more generic, but it's everything we make. Take a moment to convince yourself that this true is the same as this true that I've written it using more standard Python notation, right? So what does true say? True says, give me an x, I'm going to return a function. That function says, give me a y, I return x. So that's the Lambda calculus true. Here's the Python true. I'm defining a function, f, dedicated to f. It takes a y, so it just returns f, and then this Py true returns the function f. This is the currying, right? These are the same thing. And then you just follow your nose. You just read the Wikipedia article and you just translate symbol by symbol. Here's false, here's and, here's or, here's not. I don't have to put this first thing in parentheses. I just did it to make it homogeneous. Yeah, and then so here, in order to print, so if so what is true? True is a function. That's not easy to print in Python. You're going to get what? A pointer in memory where it sits or something if you're going to print that. But it's clear what true does, right? True ignores the second argument and returns the first one. So here's my little two bool, so we can print these things out and it's readable. So I'm going to say, if I have a Boolean value, I'm going to stick true in the string true in the first coordinate, false here, and compare it to the string true. So this is converting this lambda bool true and false to Python. And then we can try it out. We can do all this. We can make sure that this works. And we can do that. I'll show you some more stuff. And you can just go crazy, go nuts. You can, here's the same thing we did before, 0, successor, add, predecessor. I think I showed you that in the definition of factorial, but I didn't find it. There it is. Subtraction, multiplication. You can find 1 in terms of the successor of 0 and make sure that's the same. Lambda reduces. Here's the is 0. Here's the if then else. Similarly to the Booleans, I'm not going to go print in 1, right? That's going to be ugly. So I wrote this little thing that converts my church numerals to things that look like numerals to me, right? So what do? What does the church numeral do? It says, give me a function, I'm going to apply it 3 times, so I'm just going to pass it the function, add 1. So if it's applied 3 times, I've added 1 3 times. So now I can print my church numerals out and get nice things. And then we can test it out. We can run all this. And you can just keep going, building up math. Pairs. We can encode pairs as this thing. Here's the projection onto the first coordinate, projection onto the second. Here's an example pair, a pair of 1, 2. And then, so what should this be? Second 1, 2, that should just return 2, right? Check. Integers. How do you define integers? Well, the standard trick is this accounting trick from like 70 AD, right? Have you heard of what's called double entry something? Looking? You write your credits and your debts on one side, so you think of anytime you add a credit, you have to deduce it somewhere. This is the same idea here. How you define the integers out of natural numbers? It's a pair, right? So where you think of it as, so it's a pair of AB, you think of it as A minus B. So -1, we can write as 1 minus 2, 4, we can write as 4 minus 0, and there's integer add, and we can make sure that, I have to write a 2n function, right? So here's what I take first minus second to get my integer. And we can see a 4 plus -1 is 3. And then finally, I'll show you something I couldn't quite get to work. I don't think it's possible. Maybe there's some magic, Python magic I could have done. I almost got the factorial example working, but there's some trouble with Python being called by value. So I had to cheat a little bit. Well, first of all, the Y Combinator doesn't work in call by value. The Y Combinator just straight out breaks in call by value. But there's this nice little variant of it called the Z Combinator that works way better in a call by value language. So it won't move forever, unlike the Y Combinator. So I'm going to use Z instead of Y. Here's Python. So you remember we did that big F, we did factorial of the little f. Here's that written out in Python syntax. If n equals 0, return 1. If n equals 0, else return that thing. Here would be the pure Lambda Calculus version of that factorial function. This one I couldn't get to work, sadly. But what you can do is I can almost get it if I stick the fixed point Z in with a Python factorial, I can get it to work. I can do factorial of 4. And I get a little bit closer. Really what gets me, what I can't do, is I need a short circuiting if. I need the if to, Python's if then else does short circuit like I want. But my if then else won't when I'm trying to do this like the calculus in Python. So I had to cheat. I could almost get my pure factorial in Lambda Calculus, but I had to use Python's if then else. And it also works. So you can see I'm still using these guys in Lambda Calculus. And then, just for fun, let's do Python 3. It's really cool. Yeah, you can scroll up and you got true and false is false, pi true and false is false.
It's really fast.
Hopefully it all worked. 4 plus -1 is 3.
That's great. Oh, yeah.
Factorials worked. Yeah, it's just runs in Python. And then I think I'll just wrap it up. Well, actually, questions? Any questions? Anyone want to see the Python code? There's probably a lot to take it at once.
How long did it take you to write the program?
This didn't take too long. Once I figured
Define
out.
too long.
Huh?
Define too long.
A couple hours? Well, okay. A couple hours to figure out how to, I don't know, an hour to get it, kind of figure out how to do Lambda Calculus in Python. And then super quick to just copy paste from Wikipedia and translate. And then I probably just don't want to admit how long I spent trying to fiddle with factorial. Thanks for for sure.
Pretty cool.
Thanks. But yeah, so you can just read stuff off Wikipedia and do it like this, and you can see it in action. So if you want to look at this, it's also nesting the code. Play around with it yourself. to get that factorial working, that'd be cool. I suspect it's a hard stop. Anyway, so here's my final takeaway. Lambda Calculus boils computer science down into these three things: variables, abstraction, and application. So it's like the ultimate Occam's razor for computation. If you want to design a new programming language and you want to try out a feature with as minimal cruft as possible, this is as good as it gets. You can try adding stuff onto Lambda Calculus, play around with what it looks like at the bare bones, and this is a great place to go. So things, if you're interested in it and you wanted to learn more, well, first of all, I guess I should have I just realized here I didn't have a reference for Lambda Calculus. If you do want to read, there's lots of really good books. There's this one big tome that's really excellent. It does everything carefully. I think it's called Lambda Calculus by Hank Barendale. It's awesome, but there's tons of good stuff on it. If you were to want to learn more, the next, God is not here from the rear barn, but I would say, the next fun thing is adding types to this. This is something actually Church did right at the outset. He was playing the types right at the very beginning, trying with types, without types, doing different stuff. It's very interesting to add types to it. And what pops out of that is this notion, and this is a talk in and of itself, propositions as types. And this is sort of a metaphor that you can make concrete. Earlier I was talking about how a lot of the inspiration for this came out of people trying to write what a proof was, and they knew a proof needed to be algorithmic, it needed to be checkable. Well, it turns out that there's this great correspondence between the type of a program and propositions, like statements you want to prove. And so a proof of that proposition ends up being exactly a program that implements that type. So, like the identity function, right? What's its type? It's like A to A. It proves the proposition if A, then A. Very interesting proposition, but then neither is the identity function. And if it's not there, that would be cute. But it goes on and on. As you add more interesting, the Lambda Calculus has tons of interesting abstractions you can add to it. And the metaphor just keeps continuing. To the point where you'll see repeatedly in the literature stuff invented in logic that ends up being invented independently in computer science and vice versa. So you almost get a theorem for free in another discipline every time you get one. It's very interesting. And there are fun talks on propositional types if you want to find. That's it.